Hello everybody. In this session, I'll cover the parallel command session. I'll also describe a parallel command session by using its abbreviation, PCS. A PCS is useful for modifying a design by changing multiple features without the risk of losing the initial state of the design if the changes are not desired. This is a multimodal function available in CATIA Icem, where you can stack multiple commands in a single session. A PCS is also an efficient way to work because with the multimodal commanding, it eliminates the necessity of validating a command prior to entering any subsequent feature. But before diving into its functionality, let me set up the scene. So in this mockup, there are three main global surfaces: a windshield, roof, and side. These are all datum surfaces, and as you can see, with a double click, our control points are activated. These surfaces drive several features, such as a roof to windshield blend, an A-pillar blend, and finally, an advanced fillet between our roof and side surface. If you're familiar with CATIA, then you already know the typical workflow. For example, in this part, I can easily make a change to a feature like this roof to windshield blend. So I am going to pull on the roof limitation boundary, stretching it rearward. And you may notice that the corner blend to its right also updates. This is the standard power of CATIA feature-based design. Okay, I'm just going to undo that modification to revert back to the original state. The green flags on the screen are matching constraints. These are used to ensure that the boundary conditions of our three global surfaces stay aligned if a change is made. It's important to note, use extreme care when choosing the source and targets of a matching constraint. So in this case, our roof surface is the main target of all three matching constraints. So this means a modification from the roof will force both the windshield and side surface to adapt their boundary positions. I'll show an example of this shortly. So we saw the normal mode of the feature modifications. Now let's take a look at how we can work inside a parallel command session. The command is inside the Tools toolbar at the top left of my screen here, and it kind of looks like a recycle icon. When I enter into it, a dialog box pops onto my screen. The tab on the left that reads Running Commands is activated, so I just need to double-click features to bring them into the session. You can do this by selecting the geometry itself or in the tree, which I am doing, starting with the roof to windshield blend surface. Next, the A-pillar blend, the roof to side advanced fillet, the corner blend, and finally the roof surface control points. Now let's take a look at the Options tab, starting from left to right. The first option hides all the feature dialog boxes in your session. The next option will show only the focus command dialog box. The focus command is chosen from the Running Commands interface. The first manipulator option hides all the manipulators, which I don't see the point of using. And the last option will show only focus command manipulators. I just leave these last two unselected. And as you can see, the control point dialog box is shown on my screen as the feature itself is highlighted in orange inside of my running command list. So as I switch my selection through this interface, you can see that the dialog boxes are synchronized. This is my recommended workflow, with an exception that I will show in the next example. I have 5 features in this PCS, all showing detailed information, making the screen look a little bit cluttered. So in this case, I'm just going to go through each dialog box to unselect the detailed information. Okay, let's start a change by activating the control points on the roof. I'm going to pull the leading edge down in Z direction by 25 millimeters. You can see that all my matching constraints and features update. At this point, there's no differentiation of making the change when compared to the conventional method, but here's where a PCS makes a difference. Now I activate the corner fillet, bringing up its dialog box and controls. So the first thing I do is pull the left side upper support surface blend limit. And let's just rotate the view so we can see the corner blend a little more clearly. So now I slide the other limit towards the rear. Next, I want to modify the fillet value on the roof to side surface fillet. I'm just going to increase the value from 150 to 200 millimeters. And now let's take a look at the A-pillar blend. Pulling the side surface limit a bit rearward, stretching the surface out just a bit more. And the last change is to the roof to windshield blend, where I want to pull the roof limit rearward. Okay, those are all the changes I want to make, but now is the time where an executive decision needs to be made. If I want to keep the changes, I click OK and they are all recorded in our history tree. But if I do not like the modifications, then this is a great opportunity to abort the session. And I do not like what I just did here. So I just click on cancel and my original design is restored. Okay, in our next example, we cover matching constraints in a parallel command session for the corner fillet surface. The first thing I need to do is set up 4 inside matching constraints for the 2 side fillets. These matches will not be needed for the parallel command session, but can still be factored into the changes that are made inside the session because they are directly impacting the corner fillet. So these are all inside matches with G2 continuity imposed. Now I enter into an empty PCS and create new features. So I want to start with a new G1 edge matching constraint, targeting the left side boundary to the adjacent fillet boundary. I want to slide the dialog box to the left side of the screen, then start a new matching constraint. The new matching dialog box, it appears directly on top of the prior one, so I'm just going to slide this to the right side. And just as a reminder, I have all options turned on to show all of the dialogues. Now I impose the matching constraints to the opposite side boundaries. And so far it's looking pretty good. I see the green flag, which means that my tolerances are kept. Now I want to create an inside match constraint for both the top and bottom boundaries to their targeted support surfaces. Let's start with the top boundary. I am sliding the dialog box to center left and slightly higher than the others. Still looking good at this point. And finally, the bottom edge constraint. Sliding this dialog box down and on the center right. Laying these out in this manner helps me map out the dialogues to the part. And now I want to turn on the furtive display, which is located inside my Tools toolbar. This shows the patch structures. Okay, so taking a look at our bottom matching constraint, we can see that it is out of tolerance. So the first thing that we need to investigate is the deviation distance. The information for this match is shown inside our center right dialog box, and we can see that we are close to 0.5 millimeters out of tolerance. So my first step is to apply the constraint and see how close we can get. Not too bad. We are actually okay with G1 and within 0.003 millimeters G0, but we need to do a little better. And this is where increasing the order of the corner fillet can help. So I increase from 6 to 7 orders and apply. And we can see that we're within 0.002 millimeters. So let's do another increase from 7 to 8 orders and apply. Okay, we're close. We're 0.001 millimeters. Let's increase it to 9 orders and apply. Okay, that did the trick. But in the process, we just destroyed our end matches. And this is where it's an advantage to use a parallel command session because I have instant access to all the dialog boxes to quickly find out what's wrong. This scenario is kind of like chasing an air bubble. When I make one correction to a match, it destroys another, and vice versa. So, this just tells me of 2 possible causes. One, the adjacent fillet is out of tolerance to its support surface, or two, there is a sliver gap or maybe an overlap with the corner fillet edge to the adjacent fillets. Now we know it's not the first option because the parent fillets are matched to their support surfaces. So let's take a closer look at the end conditions. Let's start at the left side. Now looking at its dialog box, we see a deviation of 0.5 millimeters. And as we zoom in a little closer to the area, it shows that the corner blend would need to go beyond its support surface to complete the match. But by doing so would render the inside match out of tolerance, as I'm showing here. So I reapply the bottom match and zoom out, verifying that the fillets are in fact good to their support surfaces, as you can see. The issue is that the fillet needs to be positionally matched to the corner fillet. We can easily fix this by clicking on the invert button of our edge match. This switches the source and target surfaces. We must only impose G0 to align the boundary to the corner. Next, we apply the change. Now that G0 is good, click on the inverse again and retry G1 between the two surfaces. Good. And now we just repeat the process for the other side. Invert the source and target, G0 match, inverse one more time, and then move to G1 to achieve tangency. And now that we have all these green flags, we can strive further to obtain G2 continuity with the top and bottom inside matches. And there you have it. So to wrap up this topic, you saw how a parallel command session is useful for prospecting ideas with multimodal commanding, and its strength in quickly resolving multi-matches in an elegant manner for real productivity gains. Thanks a lot.